This demonstration is particle size analysis in the soil, ASTM D422. We need to know the grain size distribution in soil so that we can classify it according to the Unified Soil Classification System. The particle size analysis test involves two main parts. Part 1 is the mechanical sieve analysis, and Part 2 is the hydrometer analysis. Let's start with the mechanical sieve analysis. The mechanical sieve analysis involves placing some oven-dried soil. Here I have approximately 750 grams of oven-dried soil. We're going to take that soil and we're going to pass it through a stack of sieves. The stack of sieves starts with coarse sieves at the top and finer sieves at the bottom. Here I have a number 4 sieve at the top with a mesh opening of 4.75 millimeters, a number 10 sieve below that with a mesh opening of 2 millimeters, a number 40 sieve below that with a mesh opening of 0.425 millimeters, and a pan below that to catch everything that passes through the number 40 sieve. So the first thing that we do is we obtain the net mass of our soil. This is, again, oven-dried soil, approximately 750 grams. The net mass of the soil before sieving. And we'll refer to that as M total. The next thing we do is we're going to take that soil and we're going to pass it through the stack of sieves. We're going to just pour it into the top and we're going to shake it. Now you can shake it by hand for about 10 minutes, or alternatively you can place it in a mechanical shaker and shake it for maybe about 5 minutes. This is a mechanical shaker. So we lower it down, lower the top down, clamp that up like that. Get it nice and tight. Probably a good idea to have some ear protection because this is pretty noisy. And maybe even some eye protection, because there might be some flying dust and debris. And we're going to shake it for 5 minutes. Okay. Now that we've shaken our material for 5 minutes, we're going to obtain the mass of each fraction within the stack of sieves. Now the first thing we do is we obtain the net mass of the material that passed the number 40 sieve. So let's take our bowl and we can zero out the scale and we can obtain that net mass. That we'll refer to as M minus number 40, the mass of the material that passed the number 40 sieve. Now we're going to take this material and we're going to set it aside because this is the material that we're going to use for the hydrometer analysis. We'll just put it up there for now. Okay. So now we're going to take the material that's sitting on top of the number 40 sieve. This material passed the number 10 sieve. So we're going to obtain its net mass. So we can record the net mass of the material that passed the number 10 sieve We can add that, if we add that to the net mass of the material that passed the number 40 sieve, that is all of the material, that sum is all of the material that passed the number 10 sieve. So we can add those two numbers together, and we can enter that on our data sheet under M minus number 10. Mass of the material, cumulative mass of the material that passed the number 10 sieve. Okay? So now to that, we can add the material sitting on top of the number 10 sieve. That material passed number 4 sieve. So if I take the material that passed number 10 and I add the material that was sitting on top of number 10, that gives me the cumulative mass of the material that passed the number 4 sieve. That's M minus number 4. Finally, I have some material that was retained by the number 4 sieve. So what I need to do is I need to take that material, and I can obtain the net weight of that material. That's the cumulative mass of material retained by the number 4 sieve, and that is M plus number 4. You can write that down on your data sheet as well. Escaped out of one of the sides of the sieves during shaking. So what we can do is we can take the material, the mass of the material retained by the number 4 and passing the number 4, add that together. That gives us a new total, and that is M subtotal prime. What we need for the hydrometer analysis is about 50 grams of that soil that passed the number 40 sieve from the mechanical sieving analysis. So we need to obtain the net mass of that material, approximately 50.0 grams, and that is M sub D. Now chances are this soil contains clay particles. Clay particles, when in a dry state, tend to be flocculated to one another, tend to be stuck to one another because of electrical charges. Well, we want the particles to act individually, as individuals. So we want to neutralize those charges so that the particles can disperse from one another. So what we're going to do is we're going to take this soil and we're going to mix it with approximately 125 milliliters of a sodium hexametaphosphate solution at a concentration of 40 grams per liter. So we're going to take that soil and we're going to put it in there. We'll mix it up. And we're going to let it sit for 16 hours to let the sodium hexametaphosphate do its thing. Okay, 16 hours later, the particles are dispersed. So we're going to take the mixture and we're going to put it in a dispersion cup. This is a special ASTM standard specified cup with bafflers on the inside. We're going to take the material and we're going to make sure we get it all into the cup. Now there's probably going to be some solids remaining in the bottom of the beaker. So we'll use a squeeze bottle with distilled water and we're going to squeeze that down. Get all the solids into our dispersion cup. There we go. And what we want to do is we want to fill this cup to where it's at least half full of distilled water. So I'm going to take a little bit more distilled water, pour it into the cup. So now, it's a little bit more than half full. So I'm going to mix this slurry with a mixing device that operates at a rate of approximately 10,000 RPM. ASTM standard says that we mix it for 1 minute. No more, no less. I have a timer here, so I can time that 1 minute. Here we go. Okay, my 1 minute is up. There might be a little bit of soil on the blade there, so I'm going to rinse the soil into the cup. Now, having added my sodium hexametaphosphate, having mixed it up for a minute with the mixer, the material should be fully dispersed. So the next thing I do is I take a graduated cylinder. There's a 1,000 milliliter etch mark on this cylinder. This is where the hydrometer measurement is going to happen. So what I need to do is I need to get all of this into here. And chances are, again, there might be some sediment in the bottom. So you have to make sure to get it all out of the cup and into the cylinder. Okay. Now, I have successfully gotten all of the soil from the cup into the cylinder. You can see there's some soil stuck to the side of the cylinder, so what I can do is rinse it with the squeeze bottle. And I'm going to top this off to just below the etch mark, maybe about 1/4 of an inch below the etch mark, with some more distilled water. I have a very large beaker. There. Now it's full of the soil, slurry, the distilled water, to just below the etch mark. I think I can probably put a little bit more in there. Whoops. The reason I don't fill it all the way up, it'll become apparent in a second here. I have a stopper. So what I need to do is I need to agitate this mixture. What I want to do is I want to get all the soil solids suspended. Because what's going to happen is when I stop agitating the mixture, they're going to start settling. So I want to get them all suspended, so I agitate the mixture using a specific ASTM method. I'm going to take the cylinder and I'm going to go like this, tipping it back and forth for 60 seconds. 1, 2, 3. I'll show you. So I need a timer. I need to time this for 60 seconds. When I'm done with my 60-second agitation, I'm going to be setting it down, and I'm going to have to reset and start the timer immediately after that. So, here we go. 1, 2, 3, 4, 5, 55, 56, 57, 58, 59, 60. Reset and start. Okay, the clock is running. I'm going to take the soil that's stuck on the stopper, rinse it down, take the soil that's on the inside of the cylinder, rinse it down, and top off the water level to the etch mark. I'm at about 30 seconds or so. Now this is my hydrometer. Some weighted buckshot down here in some epoxy, graduated neck. I'm going to put it in here and it's going to float like a bobber. And I'm going to take a reading. Whereas you usually read things, water levels at the bottom of the meniscus, here we're going to read at the top of the meniscus. So when it gets close to 2 minutes, I'm going to put it in and take a reading. We're going to take readings at, I have it written down here, 2 minutes, 5 minutes, 15, 30, 60, 250, and 1,440 minutes. So here comes 90 seconds. I'm going to very carefully place it in there. I don't want it to bob up and down too much. And at a time of 2 minutes, and I'm going to record that time, I'm going to make a reading off of the neck of this hydrometer. That reading is R, capital R. So I have my timer. Here comes 2 minutes, right there, and I take a reading. So as I mentioned, you take readings at 2, 5, 30, 60 minutes, etc. Between readings, you don't want to leave the hydrometer in the slurry. Particles of soil will stick to the hydrometer, which will affect the measurement. So what you want to do is you want to take a separate cylinder of water, take the hydrometer out between readings, place it in that cylinder and give it a spin. What that does is it knocks the soil particles off of the hydrometer, and it sits there and waits between readings. Every time you take a reading, say we're ready to take another reading right now, we want to put the hydrometer back in a little bit before the time when we want to take the reading to give the hydrometer a little chance to stop bobbing up and down so we can get a steady reading. After we make all of our hydrometer measurements, we need to convert this information to particle size and percent passing for points that we can plot on our gradation curve. Particle size, or D, can be expressed as a function of R, the reading that we actually took, T, the time that we took the reading, and a parameter K, which is a function of specific gravity and temperature. Now, assuming that the temperature in the room is relatively constant and the water that we used was distilled water that didn't come from a tap, it was more or less at room temperature, we can record that temperature using a thermometer. And here I just have a thermometer in my storage water here. This is the water that I just used to store the hydrometer between readings. And I can record that temperature. And we'll use that temperature. And we'll use some assumed specific gravity of the material, or maybe a measured specific gravity, maybe you measured it. And we'll go to table 5.1 in the lab manual to come up with this parameter K. So given K, given R, and given the time, we can calculate the particle size. For every particle size data, we need a corresponding percent passing. Now this percent passing we'll refer to as P prime, the percent passing of the material that passed the number 40 sieve. So we can express percent passing as a function of R, as a function of the dry mass of the soil, that 50 plus or minus grams of soil that we started with, and as a function of a couple of other constants, B and A. B and A are a function of specific gravity and temperature, and they can be found on table 5.2 in the lab manual. So as I mentioned, these percents passing are just the percent passing corresponding to the material that passed the number 40 sieve. If we want to combine these data points, with the data points that we got from our mechanical sieve analysis earlier, we'll need to take all of these P prime values and we'll need to multiply them by the percent that passed the number 40 sieve from that previous test in order to get true percent passing values that we can combine with the other ones from the other test. That concludes the particle size analysis demonstration. The next demonstration that you'll be looking at will be determination of material passing the number 200 sieve. We'll see you then. Thanks.